Welcome back, chemistry students. Today we're going to practice some mixed stoichiometry problems. Our first problem asks, how many liters of oxygen gas are needed to react completely with 13 moles of methane CH4 at standard temperature and pressure? We are given 13 moles of methane. We want to find liters of oxygen gas. So we're going to go from moles of methane to liters of oxygen gas, and we're going to use mole ratio. We're also going to use the conversion 22.4 liters of gas is inside 1 mole of gas. We're going to start with what we're given, which is 13 moles of methane. We want moles of methane to cancel, so we need that to be in the denominator in our next step. So we're going to use mole ratio. If you look up at the balanced chemical equation, there is no coefficient for methane, which we assume there is a coefficient of 1, representing 1 mole. And then we're going from methane to oxygen gas. That's our ultimate goal. And so we want to look at the coefficient for oxygen, which is right here. So it is going to be 2 moles of oxygen gas that goes in the numerator. So now moles of methane cancel. Our next step, we want moles of oxygen gas to be in the denominator, and we need to go from moles of oxygen gas to liters of oxygen gas. So we're going to use our conversion factor, 22.4 liters of oxygen gas and 1 mole of oxygen gas. So now moles of oxygen gas cancel, and we are left with liters of oxygen gas, which is what we ultimately want. So if we plug this into the calculator, we're going to get 582.4. We're limited to 2 significant figures, so that takes us to 580 liters of oxygen gas. The next problem asks, how many grams of iron will react with 225 liters of oxygen to form rust? Then they give us a balanced chemical equation. We are given 225 liters of oxygen. We're trying to find grams of iron. So let's start out with what we're given. 225 liters of oxygen gas. Our next step, we want liters of oxygen gas to be in the denominator. We're going to try to get from liters to moles, which will then take us to the mole ratio, and from that step we'll be able to get to grams of iron using molar mass looking ahead. And so we want that 22.4 liters of oxygen gas in 1 mole of oxygen gas to be the next step. The liters of oxygen gas are going to cancel. In the next step, we want the moles of oxygen gas to cancel. We want it to be in the denominator. So we're going to go from moles of oxygen gas to moles of iron. So we're going to use our mole ratio. So if we look up at the balanced chemical equation, we're going to be looking at this coefficient, 3, for oxygen gas, and then this coefficient of 4 for iron. So when we plug it into the problem, we're going to have 3 moles of oxygen gas for every 4 moles of iron. Moles of oxygen gas cancel, and now we're at moles of iron. We ultimately want to get to grams of iron. So to get from moles to grams, we can use molar mass from the periodic table. So 1 mole of iron, how many grams? Well, we look to the periodic table, 55.85 grams of iron in 1 mole of iron. Moles of iron will cancel. We're left with grams of iron, which is what we want. So when you plug it into your calculator, we'll be limited to 3 significant figures, and that takes us to 748 grams of iron. Number 3 asks, how many liters of oxygen will react completely with 58 grams of propane at standard temperature and pressure? We are given 58 grams. We're trying to find liters of oxygen. So we're going to start with what we're given, 58 grams of propane. C3H8 is propane. So we want grams to be our next step in the denominator. And so we're going to use molar mass to get from grams of propane to moles of propane. So to get the molar mass, we look to the periodic table. Carbon is 12.01 grams. We have to multiply that by 3 since there are 3 carbons. And then hydrogen is 1.008. We have to multiply that by 8 because there are 8 hydrogens, and we add that together to get 44.09 grams. That's what we're going to plug into the denominator. So at this point, our grams of propane cancel, and we're left with moles of propane. So the next step, we want to get from moles of propane to moles of oxygen gas. So we're going to need to use our mole ratio. So if you look, the coefficient for propane is 1. For oxygen, it's 5. So when we plug it in, 1 mole of propane is going to go into the denominator, and then 5 moles of oxygen gas are going to go into the numerator. Moles of propane cancel, and then we're left with moles of oxygen gas. So we want to get from moles of oxygen gas to liters of oxygen. So we can use our conversion factor of 22.4 liters in 1 mole in our next step. So 1 mole will go into the denominator, 22.4 liters will go into the numerator. Moles of oxygen gas cancel. We're left with liters of oxygen, which is what we ultimately want. When we plug this into our calculator, we're going to be limited to 2 significant figures. So the calculator answer will be 147.335, and it keeps going. We round that to 150 liters of oxygen gas for our final answer. 4 asks, how many molecules of ammonia are produced from 3.0 liters of hydrogen reacting with excess nitrogen at standard temperature and pressure? We are given 3.0 liters of hydrogen. We're trying to find molecules of ammonia. So we're going to start with what we're given, 3.0 liters of hydrogen gas. We need to get from liters to moles in our next step. So in the denominator, we're going to have our conversion, 22.4 liters of hydrogen gas and 1 mole of hydrogen gas. Liters of hydrogen gas cancel. In our next step, we want to get from moles of hydrogen gas to moles of ammonia. And so to get from hydrogen to ammonia, we use the mole ratio. So this 3 comes from the coefficient in the balanced chemical equation for hydrogen gas, and then the 2 comes from the coefficient for ammonia in the balanced chemical equation. So moles of hydrogen gas cancel. Our next step, we want to get from moles of ammonia to molecules of ammonia. So in order to do that, we need to use Avogadro's number. So 1 mole of ammonia is equal to 6.02 times 10 to the 23rd molecules of ammonia. So our moles of ammonia are going to cancel. We're left with molecules of ammonia, which is what we ultimately want. So when we do the math, we're limited to 2 significant figures. So your final answer is going to be 5.4 times 10 to the 22nd molecules of ammonia. For number 5, it asks how many grams of carbon dioxide will be produced from 6.2 moles of benzene, C6H6, burning in the presence of excess oxygen, and they give us the balanced chemical equation. We are given 6.2 moles of benzene. We are trying to find grams of carbon dioxide. And so with mixed stoichiometry problems, it's really important to be able to identify what you're given, where you start, and then what you need to find, where you need to end up, because they all require different steps based upon what you're given and then what you're trying to find and where you're trying to end. And so it's important to label those things before you start. 6.2 moles of benzene is what we're going to start with. We want moles of benzene to be in the denominator. So our next step is going to be our mole ratio. If we take a look at the equation, benzene has a coefficient of 2. That's going to go in the denominator. We're trying to get to carbon dioxide, so we're going to use the coefficient of 12 for carbon dioxide. So when we plug that in, 2 moles of benzene will go in the denominator, 12 moles of carbon dioxide will go into the numerator. Moles of benzene cancel, and right now we're at moles of carbon dioxide. So we want to get to grams of carbon dioxide. To get from moles of carbon dioxide to grams of carbon dioxide, we're going to use molar mass. So on the periodic table, we're able to find the molar mass for carbon dioxide by taking 12.01 grams plus 2 times 16 grams, since there are 2 oxygens, to get 44.01 grams. Moles of carbon dioxide cancel, and we are at grams of carbon dioxide. So we can plug everything into our calculator. We're limited to 2 significant figures. So it comes out in our calculator to be 1,637. We have to round that to 1,600 grams of carbon dioxide gas. Number 6 asks, how many liters of nitrogen will be produced from 16 liters of ammonia reacting with excess oxygen? So we are trying to find liters of nitrogen. We are given liters of ammonia. So how do we get from liters of ammonia to liters of nitrogen? That's what we need to ask ourselves. We're going to start with 16 liters of ammonia. We want liters of ammonia to be in the denominator of the next step. So we're going to need to go from liters to moles so we can use our mole ratio. So there are 22.4 liters of ammonia in 1 mole of ammonia. And so the liters of ammonia cancel. And now in the next step, we're able to use the mole ratio. If we look, ammonia has a coefficient of 4, and nitrogen has a coefficient of 2. So that will help us with the mole ratio. 4 moles of ammonia will go in the denominator. 2 moles of nitrogen gas will go in the numerator. Moles of ammonia cancel, and we're left with moles of nitrogen. We need to get to liters of nitrogen. So to get from moles back to liters, we're going to use our conversion factor again, except this time moles of nitrogen, 1 mole of nitrogen, will go into the denominator, and 22.4 liters of nitrogen gas will go in the numerator. The moles of nitrogen gas cancel. We're left with liters of nitrogen. So when we plug it into our calculator, we are limited to 2 significant figures. And so we round it, or it comes out to be 8. So we have to make it 8.0 liters of nitrogen gas to have the correct number of significant figures. Last problem of the lesson. How many grams of phosgene, Cl2CO, will produce 1.22 grams of hydrochloric acid, HCl, in the presence of excess water? We are given 1.22 grams of hydrochloric acid. We're trying to find the grams of phosgene. So 1.22 grams of HCl is what we're going to start with. The next step, we want grams of HCl to be in the denominator. We want moles of HCl to be in the numerator. So we're going to need to use molar mass to get from grams to moles. So on the periodic table, the molar mass of HCl comes out to be 36.46 grams in 1 mole. So grams of HCl cancel, and we're at moles of HCl. Our next step is going to be the mole ratio. We need to get from hydrochloric acid to phosgene. So HCl has a coefficient of 2, and then phosgene has a coefficient of just 1. So we can plug that in, HCl being in the denominator, 2 moles, and phosgene being in the numerator, just 1 mole. Moles of HCl cancel. So now we need to get from the moles of phosgene to grams of phosgene, and we're going to do that by using molar mass. So moles of phosgene will be in the denominator, which means molar mass has to be in the numerator. So when we find the molar mass on the periodic table, you can see how I worked it out on the bottom of the slide. It comes out to be 98.91 grams. Moles of phosgene cancel, and then we're left with grams of phosgene. We need to make it 3 significant figures when we round. So it comes out to be 1.65 grams of phosgene as our final answer. You're going to be practicing these skills on a University of Texas assignment, and all of the questions on the University of Texas assignment are similar to what I've presented here. So you can go back if you're confused and work through some of these problems as I narrate it, and that should help get you through the assignment.